Alright, so next section, section 13.5. Lines and planes in space. So, as an analogy, it's like the first time you learned rise over run and then the equation of the line, that first exposure to analytic geometry. So this is like the continuation, the first steps into analytic geometry, but in 3 dimensions. And well, actually, we already did a little bit of this at the end of the semester in Calc 2 when we looked at parametric equations, how even paths that don't look like a function that failed the vertical line test, well, they became functions if those were defined in a different way. In fact, when we define them as functions, as the pattern or the path of a particle over time, well, in that case, we define that the particle is never in the same place. It's never in 2 places at the same time. Well, so those were parametric equations. Plus any other detail. So the thing here is that we can extend this and come up with parametric equations, but in 3 dimensions. And well, to begin with, in this case, we're going to start with the simplest type of functions, which is the linear function. Again, coming back to the analogy, when you first learn the linear functions, and then quadratics, cubics, radicals, etc. Those are coming in the next chapter, in chapter 14, when we go more in depth into vector valued functions, not just the algebra, but also the calculus, derivatives, integrals, and the like. All right. Well, so in this case, in 2 dimensions, we got this notation, the x sub t and y of t in parametric form minus the diamond parentheses. But of course, we can rewrite this using the ij notation. And in 3 dimensions, we'll just add the z function and a product with the vector k in the direction of k. All right. So, in this case, well, we are going to look at functions of 1 variable. Functions of 1 variable will describe or will define curves. Later in the next chapter, we're going to look at spirals and other functions that define pretty cool patterns. However, multivariable functions in the parametric forms will define surfaces. We may look at some of this at the end of the semester when we look at surface integrals and flux integrals. Well, you'll see when we get there. So, but in the meantime, so the other thing here is, well, because we're defining a line, and well, the 2 elements to come up with the equation of a line are a point and a slope. However, it's a little weird in the 3-dimensional space because we don't have a slope in there. Well, technically we do have a slope. However, we have slopes in technically infinitely many directions, but those are defined in surfaces rather, because if you think about this setting, we can have a slope in the x direction, a slope in the y direction, or a slope in the z direction, but those are not the only 2 directions in the 3D space. Actually, we can have slopes in every direction, and that's something we're going to do, I think, also in chapter 14, the directional derivative and the gradient in this case. So, in the meantime, well, how are we going to deal with the slope anyway? Well, so instead of having a slope, if you relate this x naught plus at, well, rearrange it as at plus x naught. Doesn't that really look like mx plus b? Like the linear equation? But in this case, that slope, instead of having a slope, those are going to be the components of the vector in the same direction as the line that is expressed or defined in parametric form. And of course, recall that this vector, this direction vector, is a free vector, can be anywhere, right? As long as it's in the same direction and has the same magnitude as that on the line that we're parameterizing. And well, in this case, we need an initial point. That initial point is going to be a fixed point from the origin to any arbitrary point. That will be a given point. All right, so that's how we're going to describe this equation, not with a slope and the point. We're still going to use a point, but in this case, a vector that goes in the direction of the line, not the slope. All right, so let's look at one example, how to find the parametric equation of a line. Some restrictions, well, depending on the context, on what we are talking about. So, well, find the vector equation and the parametric equations for the line L that passes through the points A3, 1, 2, and B, 0, 5, -3. All right. Of course, we have an initial point. That's point A, right? What else do we need? A vector. Right? Not the slope in this case, but the vector in the direction. But we can find the vector by subtracting terminal minus initial, right? So the vector AB will be 0 minus 3, which is -3, 5 minus -1, careful, that's positive 6, -3 minus 2, that's -5. All right? So in this case, let's write down the equation. That's x of t, y of t, z of t. First in symbols, x initial, y initial, z initial, plus a, b, and c, and t. And well, this will be 3 minus 3t, and that's the x-coordinate of the initial point, and then -1, which is the y-coordinate of the initial point, and plus 6 times t. The 6 is the component of the vector from AB, and 2 minus 5t. All right, so the numbers that multiply the variable t are the components of the vector, and the constants, the free constants here, or the constant terms, are the coordinates of the initial point. Okay, what else are they asking us to do? Okay, number 1, let's write it in this case as a vector valued function. That's another way to write it. So r of t and that's 3 minus 3t, comma, -1 plus 6t, comma, 2 minus 5t. All right, that's just a vector valued function. That's the x component, the y component, the z component, and that's related with the x equation, the y equation, and the z equation.
What wording what wording let you know that you were looking for that? Because you're saying vector valued function.
Vector. So it's a function in vector form. I don't think it says here, but we're doing this so we can get to the next examples as well, and we're gonna another way to write this kind of function. So in terms of two terms, one vector for the constant terms and plus t times -3, 6, and -5. Doesn't that look like the mx plus b in a way? But in this case, those coefficients m, the coefficient m and the constant b, are not just numbers, are actually vectors in 3D. All right. So that's the vector representation of the line that passes through those 2 points. And the second part of the problem, modify the vector equation to represent the line segment, and then what's the value represents point B. Okay, what is this equation that we just found? This is an equation that just goes on forever in that direction, in the direction of that vector, through -3, 6, -5. You know, we can plug in our favorite values of t to find out what vector is it at a given point, at a given time rather, at a given value of t. However, since this line goes on forever, that's not a segment, right? A segment it's actually only a portion of a line, in this case A and B. Now, how do we modify this equation? So R of t, so I'm going to rewrite the equation actually. I'm just going to rewrite it. Okay, I'm going to write the first version. Okay, so the best way to go about this is to compute R of 0. What's R of 0? What do we obtain when we substitute 0 over here? Well, 3 minus 3 times 0 is going to be 3. -1 plus 6 times 0, that's a -1. And 2 minus 5 times 0, that's a 2. All right? That's actually the vector that corresponds to the first point, right? What happens if we evaluate r equals to 1? Okay, so 3 minus 3 times 1, isn't that a 0? -1 plus 6 times 1, is that a 5? And 2 times a negative, 5 times 1, is that a 2 minus 5, -3? Okay. Isn't that vector in the same position as the terminal point? All right. So in this case, we got that domain for the function. So in this case, this is for all t, for your favorite value of t. But in this case, we need one for the segment. For the segment A, B. All right. For the line segment B, we only add one tiny piece of information. In this case, we need to state that we restrict this for t to being between 0 and 1. All right. It's like restricting the domain of a function, like in pre-calculus, like in algebra, to define only to define certain interval of points. In this case, the first part of the problem was just to define a general equation for our favorite value of t, and then one for the interval 0 to 1 to represent only the segment containing the points from which we define the vector. All right? And well, the last piece of information, what value of t represents point B? Isn't it t equals to 1? Yep. Yes.
So if we were given like 2 other points defined, what we could do is just like take that first number, like 0, set equal to 3 minus 3.
Exactly. Or keep plugging numbers until we get, for example, if we were given, yes, maybe 1 additional point or 2 additional points. Mm-hmm. Yeah. That's what we would do. All right, let's see. So, well, we need a vector. We don't have a vector, but we have information to come up with the vector P initial to P1. And that's subtracting terminal minus initial. And well, even though it doesn't explicitly say from initial to terminal? Well, we go with the subscript 0 to 1. That's going to tell us which one is the terminal and which one is the initial. So 3 minus 2, that's a 1. And negative 1 minus 5, that's a negative 6. And 4 minus 6, negative 2. Alright, so we got the vector. Let's write this as a vector valued function. Let's use component form. So that's going to be the initial point and the coefficients of the vector in the direction of those 2 points times the variable t, in this case plus t, and 5 plus, or rather minus 6t, and 6 minus 2t. Did you get that as an answer? Mm-hmm. Okay, another way to write this as well, using, so 2 plus t in the I direction, plus 5 minus 6t in the j direction, plus 6 minus 2t in the k direction. Either way. So, and the reason why I'm writing both versions is so we get used to both notations. On the MyMathLab homework, you may be asked for one form or the other, right? So either way. So, but also on the exam, I will specify which version I'm asking, or maybe to write both. Okay. Let's look at another example, number 3. Find the equation of the line in vector form that passes through the origin and is perpendicular to both u and v. Okay, again, the 2 pieces of information that we need to come up with the parametric form of a line is the initial point, which we got, and a vector. Was it? And a vector. But wait a minute, we have 2 vectors. What can we do with those 2 vectors?
Cross product?
The cross product. Why is a cross product?
It's perpendicular?
Because it has to be perpendicular to these 2 given vectors, right? So what do we have to do? First, find the cross product. U cross with V. And that's I, J, K. That's going to be 1, 1, 5. 0, 4, 0. And I'll give you the result of this vector. Okay? So, after doing the cross product, that should give us 20i plus 0j plus 4k, which in component form is 20, 0, 4. All right? So now we got the vector that we were looking for, which is the vector that will go perpendicular to that point, all right? Or perpendicular to the given vectors. Okay. So, well, R of t will be, in this case, well, passing through the origin. Well, so this is simply 0, 0, 0.
Could it be negative 20?
Negative 20.
You pass it on the way back and you subtract them or no?
Yes, we subtract them on the way back, but I still got positive. So did you guys get any negative? You're getting negative? Interesting. Okay, you know what? Let me do the whole thing according to my notes. Yeah. Just to make sure. IJ 1014. So that's gonna be okay, I times 1 times 0, that's a 0i plus 0j plus 4k and minus 0j 20i. Oh yes. Yes, you guys were right. Oh, wait a minute. No. I was missing the sign. Whoa. Because I think there was a typo on the problem ultimately. This one has to be -5. That's why. Yep. So typo. So 20i plus 0j. Yeah, that's fine. And that's 2004. Okay. So what about this type of, there's something very particular about the vector that we obtain. So the thing here is that we can write this in multiple forms. This is the final answer, this vector right here, that's fine. However, well, because of this 0 vector that represents the initial point, well, we can not write that vector because it's all 0. Or if we put together 20 plus 0, okay, that's just 0, t, 20, 0, and 4. Okay. Another way to write this . Another way to write this, okay, do you notice anything about the components of that vector? We can in a way reduce to lowest terms. It's valid in this case. Why is this fine? Because, well, in this case we're really not caring about the magnitude of this vector. We're only caring about the direction. So it doesn't matter, the line will go in the same direction, 20, 0, and 4. It goes in the same direction as the vector 5, 0, and 1, because ultimately this vector is 4 times the reduced vector. So it doesn't matter if we write this as a final answer or the other answer. So my MATLAB algorithm will take these answers either way. And well, also as another comment, you don't have to reduce to lowest terms that vector. That's fine. That was only a comment about that it doesn't matter if you have larger component, a multiple of the vector, because the direction is still the same, right? It's still going on the same line. All right, let's see what's next. Finding points of intersection between two lines. Well, another very classical problem in beginning algebra when you found was to find points of intersection between two curves or two lines, right? What do we do to find the intersection between two curves in general? Set equations equal to each other. So this is what we're going to do in this case. We're given two lines, well, one defined in terms of S and the other one defined in terms of R. All right. Well, in the case of the functions in two dimensions of Cartesian function, well, we only had one variable and we put together the two equations. That was it. In this case, we're going to do the following. We are going to set component by component, the x component with the x component, the y component with the y component, and the z component with the z component. So let's go ahead and write that down. So number one step, let's set up the equations. So what do we have? X of t equals to 3 plus 2t, y of t equals to negative t, and z of t equals to 5 plus t. On the other hand, let me write down right next to the equations for the second equation, which is uppercase R, but in this case it's a function of s. Okay, I need to be very careful here because my 5s look like s's, so if there's anything unclear, let me know. Okay, so 8 plus s. Okay, I'm gonna do a little curvy s so to distinguish it from my 5s. Y of s equals 2s. Z of s equals 4 minus 3s. Okay? So all we're doing is just changing the notation so we can set the quantities together. All right, so this is what we're going to do. Let's highlight. So the points of intersection, we're going to set this 3 plus 2 equal to 8 plus s. And on the other hand, we're going to set negative t equal to 2s. And that's going to be enough for now because we're dealing with two variables. So setting two equations is enough. All right. If we had three variables otherwise, well, we would have set a system of equations with three equations and three unknowns. So that's negative t. Negative t equals to 2s. Okay, if we observe this system, well, we can easily solve for t over here. Yes, I'm missing the t here, right? Yeah. So t equals to negative 2t. And okay, let me highlight so you can see what I'm going to do. I'm going to substitute this negative 2t. No, negative 2s, 2s, right? 2s, yes. 2s, negative 2s. Okay. Right here, where it corresponds for t. All right. So, let me go about that. That'll be 3 plus 2 times negative 2s equals 8 plus s. And that's going to give us 3 plus 4, or rather minus 4, s equals to 8 plus s. Okay, s on the left hand side, numbers on the right hand side, so that's negative 5. S equals 5, and s equals to negative 1. Okay, so we already got the value for s. We may go back to the second simplified equation to find the value of t. Right? T will be then negative 2 times negative 1, which is t equals to 1. All right, so far so good?
T equals 2?
T equals to, yes, t equals 2. Yep. T equals to 2. Yep. Okay, so we have the two values of s and t. But so far, we have only set equal the x component and the y component. So before we can call this a point of intersection, or before we can use this as a point of intersection, we need to verify the z equation, the z components of both equations. Notice the z equation for the z component for the first equation depends on t, while the z component of the second equation depends on s. So we need to verify with the corresponding values of s and t, so we can call it a point of intersection. So that's number 3. Verify. Verify number 1, z of what's the value of t? We got 2, and z of the value of s, in this case, negative 1. And these two correspond to r of t, lowercase, and big R of t respectively. I'm noting everything just so you can see where are these coming from. So in this case, z evaluated at 2 for the first equation, z of 2 equals 5 plus 2, which is 7, and z of negative 1, but in this case on the second equation, the one that depends on s, that's 4 minus 3 times negative 1. Isn't that a... So what do we got? That the z components are also the same. That means there will be an intersection point. If for some reason you don't get the same result when verifying the two equations, number one, double check your calculations, and if you're still getting the different results, then just say the two lines do not intersect. Which is the case. Question?
What would happen in green? Would it be R of S?
R of S. Yes. Yeah. R of S. All right, so now that we have that this is an intersection point, well, we need to find the intersection point, and there's two options to find the intersection point. Number one, plug in t equals to 2 on the three equations that depend on t, or plug in s equals to negative 1 on the three equations that depend on s. Either way you do it, you should get the same point of intersection, because surprises were obtained by setting the two equations together. Okay, so intersection point I'm gonna do the t equation, and then I'm gonna do just briefly the s equation. So x at 2, that's a 3 plus 2 times 2, and y of 2, that's a negative 2, and z of 2, that's 5 plus 2, and that's going to give us 7, negative 2, and 7. So the point of intersection is 7 comma negative 2 and 7. Let's verify using the S equation. Okay, the other alternative is to plug in S equal to negative 1 on the second set of equations. So that's x minus 1, is that a 7? Same 7. 2 times negative 1, that's negative 2. And 4 minus 3 times negative 1, that's 4 plus 3, which is 7. So it doesn't matter which one you use. You don't have to do both. As long as you do only one, that's good enough. All right. And well, these were a couple of classical problems involving lines in 3 dimensions. Let's move on to the equations of planes. That's the first surface that we discussed in 3 dimensions. Well, so a plane contains an initial point with a vector n that is perpendicular or orthogonal to that plane. Okay, let's draw a picture of that. So we got this plane. All right, that plane has some point P initial, and we are going to have, or rather the plane is going to have a related normal vector n. All right, this vector forms a 90-degree angle with every single point in the plane. All right, that we are going to call, let's just call this point Q. All right, P is the P initial here, We got that here. It's a given point. And well, when we define the equation, that's just going to be any vector. All right? Okay. How about we define a second vector? A vector that contains the same initial point as the normal vector that is orthogonal to the plane, and that point which is also on the plane, and that other vector. Do you see how these two vectors are orthogonal? Okay, if we do the dot product of those two vectors, what would the result be? 0, right? Because when two vectors have a 90-degree angle between them, the dot product is 0. Now, we need to define that vector first. So, P initial, which is, okay, I already wrote it. It's already typed. Let me write it again. And the second vector Q, which is any x, y, z. That's the variable point, and it could be anywhere on the plane. I mean, it could have even been here, all right? That point Q. And do we still agree that these two vectors are orthogonal regardless of the position of that arbitrary point Q? Okay? So, okay, how about we find the vector P initial Q? So the vector P initial Q is going to be x minus x initial, y minus y initial, and z minus z initial. All right? What are we doing? Terminal minus initial. So the initial point is a P naught, and Q is a terminal point. All right? And what about that vector n, the normal vector? Let's just give arbitrary values a, b, and c. All right? Okay, so let's find the dot product of these two vectors. So, P initial Q dotted with n. That should be, well, I'll have to rewrite all this. X minus x initial, y minus y initial, z minus z initial, and we're dotting this with the vector, with the normal vector on the plane that is normal to the plane, a, b, and c. Okay? So, because we know that these two vectors have a 90-degree angle in between them, when we multiply these two vectors, again, what are we supposed to get? 0. Okay, so this is equal to 0. All right? So to perform the dot product, we multiply the corresponding components of each vector, x with x, y with y, and c with c. What are we going to get when we do that? Okay, x minus x initial times a, or a times x minus x initial, plus b times y minus y initial, plus c times z minus z initial equals to 0. And this is our equation of the plane in standard form. All right? And that's where the equation is coming from. We have a plane with a normal vector. That normal vector is perpendicular to every single vector that you can create between this same initial point this normal vector have and any point on the plane. And well, it's all about the concept of the dot product here, keeping in mind that because the vectors are orthogonal, their dot product is 0. Now, another way to keep defining this equation What if we distribute? All right, so this will be just very quickly.
And for the standard form, there's a typo on there too.
Yes, there is. Thank you. Oh, it's a clone of it, right?
Yeah.
Yep. Okay, don't worry. B, Y, Y initial, C, Z minus Z initial. Yeah, I will fix that. This is what happens when I teach a class for the first time. Okay, so that's minus AX initial plus BY minus BY initial plus C Z minus C Z initial equals to 0. Okay, so I'm going to, okay, A times X initial, isn't that the product of just two numbers? That's a number, that's another number, that's another number. Combine the three numbers together, that's just going to give us another number. And in the end, we're going to get AX plus BY plus CZ equals whatever the addition of that number on the right hand side of the equation, that we can just call it D, which is the general form of that plane. All right. So again, the key idea here is that the coefficients, or the numbers that multiply the x, the y, and the z, are always going to be the components of the vector that is normal, that is orthogonal to that plane. We're going to be using this piece of information pretty much, I think, for the rest of the semester. Later, we're going to be multiplying other vector quantities. This will be there all the time. Okay, so let's find the general form of the equation of a plane containing the points 3, -1, 5, 2, 0, 6, and 1, 4, 2. So what do we need? Well, yes, we have three points. How can we use those 3 points? Well, number one, what are the elements that we need to find the equation of a plane? Number one, an initial point, right? Or a point in the plane. What else? A vector that is orthogonal, right? Well, in this case, we don't have any vector, but we have 3 points that can form a triangle in the same way that we solve a problem in the previous section, right? We can get 2 vectors, find the orthogonal vectors. Those are going to be the coefficients of the of x, y, and z respectively. So a picture might help. So we have the plane, and let's label A, B, and C. So we can define the vector AB, and vector AC. And if we do the cross product between those 2 vectors, we should get a vector that is orthogonal to those 2 vectors, and it's also orthogonal to the plane, and let's call it N. So let's do the cross product. Okay, so number one, before doing the cross product, we need to define vectors, right? So let's see. Okay, yes, AB. We define the vector AB between, okay, let's label A, B, and C, by the way, because it's not clear which one is which, so I have to label here. But don't worry, on the exam and also on the homework, they will be labeled. Okay? So terminal minus initial, that's 2 minus 3, that's -1. 0 minus 1, minus -1 rather, that's +1. And 6 minus 5, that's also 1. Vector AC, that's between C and A. Okay, 1 minus 3, is that a -2? and negative 4 minus negative 1. Careful with this subtraction, that should be positive 5. And the third component, that's 2 minus 5, that's a negative 3. Okay, so we have two vectors. We need the cross product to get that normal vector, that orthogonal vector. So in this case, AB crossed with AC. And again, you could have done it in a different order. You could have defined the vectors BA and CB. Well, either way is fine, but typically our reference is the first in the alphabetic order, right? We go from A to the other points. Okay, so I, J, K, and negative 1, 1, 1, negative 2, 5, negative 3. And the cross product of these two vectors, again, I'm just going to give you the result. That should be negative 8i minus 5j plus, oh no, minus 3k. All right? Okay. For the next step, well, now that we have the vector, the other piece of information that we need is a point. All right? But well, which point are we going to use? Well, number one, the picture helps. So we usually write that normal vector as having as an initial point the point A. But it doesn't matter actually. Let me tell you this. It doesn't matter if you use B as your initial point or C as your initial point, because isn't this vector N in the same direction if we write it down here or here? Well, here's kind of, or here. We're not looking for, well, the angle is the same, the direction is the same, so it doesn't matter. But again, I'm going to use point A as the initial point. So that's why I was drawing the picture as well. All right. So what do we need? Okay. So for the plane, so that's A x minus x initial plus B times x y minus y initial plus z plus c times z minus z initial equals to 0, where A, B, and C are the components of the vector that is normal. Negative 8 x minus x initial, which is the point A, x minus 3, and negative 5, so minus 5, which is the y component of the normal vector. That's y minus negative 1, isn't that a plus 1? And C, which is negative 3 times z minus z initial, which in this case is 5, equal to 0. All right, so that's the equation in what's the name of the form again? In standard form. Let's write it in the other form, in the general form, by distributing negative 8x plus 24, negative 5, y minus 5, negative 3, z plus 15 equals to 0. Okay, 24 minus 5, that's a 19, plus 15. 19 plus 15, is that a 34? Mm-hmm. So negative 8x minus 5y minus 3z plus 34 equals to 0. And let's move the 34 to the right hand side. Equals to negative 34. And of course, we can change all these negatives into positives to make this look nicer. All right. Okay, what time is it? 5 minutes. Okay, let's sketch the plane. Yes, we can do the next part in 6 minutes. Okay, sketching planes in space. Well, I think I mentioned this before. I mean, plotting in 3 dimensions, it's not that easy. However, planes are actually easy to plot using the intercepts, and in this case, and we will also label the traces of this plane, which are the lines that go in the different plane or plane, to the xy plane, the yz plane, and the xz plane. And well, so back in intermediate algebra to find, or pre-calculus, to find the intercepts of a function, you would set, well, if you wanted to find the x-intercept, you would set y equal to 0, solve for x, and if you wanted the y-intercept, you would set x equals to 0 and solve for y. In this case, well, we have 3 variables for a plane. So to get the x-intercept, we are going to set y and z equal to 0, the other 2 variables equal to 0, and solve for x in this case. So 2x plus 4y plus z, so in this case these 2 are 0. That's going to reduce to 2x equals to 8, and x rather equals to 4. So that's the value of x that will be the x-intercept. If we were to write this as an order pair, or rather as an order triple, that's going to be 4, 0, and 0. Okay? To find the y-intercept, so we are going to make 0 the other 2 variables, in this case x and z. X equals to z equals to 0. That's going to reduce to 4y equals to 8, and then y will be 2. As an order triple, that's going to be 0 to 0. And for the z-intercept, following the same pattern as before, well, we're going to set the 2 other variables equal to 0, that is x and y equal to 0. That's going to be simply z equals to 8. No need to solve anything. That's the point 0, 0, 8. All right. Now, how to plot this plane? So let me do. Let me do a 3D plane in this case. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3, 4, 5, 6, 7, 8. So we're going to plot the intercepts. 1, 2, 3, 4. This is x, this is y, and this is z. And the y-intercept, which is at 2, and at 8 for in the z direction. 1, 2, 3, 4, 5, 6, 7, 8. And we are going to connect this with lines. Right? And well, this graph right here, I'm going to shade it in a way. This will be the portion of the plane that is displayed only on the first octant. What's an octant? Well, in the 2D plane, in 2 dimensions, we have 4 quadrants. In this case, in 4 dimensions, we have 4 octants. And in this case, the first octant is the one that has all the variables being positive. All right. As for the trace as well, the xy trace. So the xy trace is a linear equation that goes in the xy plane. So if we were to look at this equation, so suppose we were in bird's eye view right here, we would see this x and y and this 1 2 1 2 3 forward. Do we agree with this picture? Okay, so that's the xy trace, and to represent the xy trace, all we do is set the z equal to 0 on the equation and simply write the rest. 2x plus 4y equals 8. And then we have the yz trace. The yz trace is this line right here when x is equal to 0. And that'll be 4y plus z equals to 8. And we have the third trace, which is the xz trace. Oh, let me label yz trace. And the xz trace. Okay, so that'll be when y equals to 0, so that's only 2x plus z equals to 8. Alright? Yeah, planes are fine when it comes to drawing them. Those are not that hard as opposed to points or other quartic surface.